The Hamilton equation becomes H is equal to del S by del Q square by 2m plus 1 by 2m m omega square Q square. Now we try to solve this equation because in terms of S here, H is equal to 1 by 2m del S by del Q square plus m omega square Q square. But H is equal to minus del L by del T. Here we get H. H here H is equal to del S by del T minus H. H is equal to minus del H by del T. You have to remember these two formulas. One is P is equal to del S by del Q and H is equal to minus del S by del T. So now putting this, we get this formula. So solving this, we get this equation 1 by 2m del S by m square plus del S by del T is equal to 0. Since the explicit dependence of S on T is involved only in the last term, here only del S by del T. And solution we can get this solution in the form as S is equal to W Q alpha minus alpha T. So that taking in del S by del T, you get one extra term alpha. Okay, T is only in this term. So I can separate this S as a function W Q alpha minus alpha T. So now our equation becomes substituting this. So del S by del T is equal to minus alpha. Here del S by del T is equal to minus alpha. So this del W by minus alpha. So from this you can say del W by del Q square because here two derivatives with respect to one T and Q. So it is very difficult to solve. So I substitute that quantity in place of S W Q alpha alpha T. So it will be alpha constant. So dw by del Q square this one. So W del W by del Q is this. Or integrating this, we can say W is equal to this dq and integrate 2m alpha root over 1 minus omega square Q square by 2 alpha. So by definition S, which is W minus alpha T, it becomes this. We can integrate this equation S as, but we have a relation in terms of alpha beta. Beta is equal to del S by del alpha. So you can find beta from this equation. Since S is this one, which is written here, S is this one, you can cancel root 2 m. So it will be root m this. So beta is equal to del S by del alpha. Take its derivative, you can get beta. So that and integration minus t. So beta plus t is equal to this one. If you integrate, you can, this is the function, so you get this easily. Or beta plus t, then for integrating, substitute this quantity as x square. This so it is root over x square, so whose integration will be sine inverse x. So finally you got sine omega beta plus t. This or q is equal to 2 over m omega square root alpha sine omega beta plus t. Okay. Similarly, you can get P. P is equal to del S by del Q. So del W by del alpha, which is del W by del Q. Okay. But we have this is our equation. So from this you can say del W directly del W by del Q will got this one. 2m alpha Q square. In place of Q, you can use the value of Q. Finally, you get P is equal to 2m alpha root over cos omega plus beta t. Okay, these are the solution Q and P using Hamilton-Jacobi method. So you have to only in this process you have to remember two formula. What I will use. First one is this one. H is equal to minus del S by del T. This formula we use here from Hamilton-Jacobi method. And second thing is P is equal to del S by del Q. Using these two formulas, we can solve this problem. Get value of Q and P. Okay. Hello? Are you getting my point? Hello? It's not difficult, but example you can understand that. We use the procedure is somehow difficult, but generally example asked. So taking one example, you can solve this problem. Find the value of Q and P. This is actually Hamilton-Jacobi method. Okay. These are other things are written. P, and in terms of this, you P and Q also get H alpha. Other things are not required to know. Even these are some problems. Okay, what is the problem? The Hamiltonian, if the Hamiltonian is independent of time, you know that conservation theorem, then it is a constant and equal to total energy. You have to remember this is the formula for conservative system. Conservative system means Lagrangian does not contain time explicitly. Means kinetic energy or potential energy independent of time. Then H is the total energy of the system. Okay. Prove that the transformation is canonical. Okay, very important. We know we have to check that Poisson bracket is one case is QP, Poisson bracket is 1, then it is transformation canonical. Another formula we have, if PdQ minus capital PdQ is an exact differential, then also the transformation is canonical. In some problem, it is very difficult to calculate its Poisson bracket. In that case, we have to follow this formula. And one example is this case. When this P1 Q is given, it is very difficult to and take more time taking to take its QP Poisson bracket and get 1. But in another way, you can solve this by showing that PdQ minus PdQ, capital small minus capital, is equal to exact differential. Means if we can write is d of some function, exact differential. Okay, use this formula PdQ minus, we have given capital Q and capital P. So capital DQ can you get here easily. So small d PQ remain as it. Q is given tan inverse Q by P. So what is DQ? Differentiate it. You get tan inverse x means 1 by 1 plus x square. So 1 by 1 plus Q square by P square. So now you take LCM, and it's Q square plus P square by P square. P square will cancel. And it is P square by 2. Okay. And P value is already given. Again, dq means we formula this. A chain rule you can differentiate it. It is basically dq means what? It is del by del q by p. Again, d of q by p. This is the case. If you calculate dq in terms of chain rule, so dq by dt means this is here d by dt. So chain rules. So this term is this, but second term dq by p is how much? U by v means v derivative u minus u derivative e by v square, p derivative q minus q d p by p square this term. So if you say this cancel, p square go to off and a p square cancel with this. So basically this is nothing but p dq minus half p dq minus q dp. Which is very easy. So which is nothing but half p dq. From p dq we subtract half p dq plus half q dp. Which is differentiation of half pq. Half pq. So it is transformation is canonical because we have to retain the differentiation of one function. Okay? Hello? Sometimes we have to use this formula also to check canonical transformation. Clear? Hello?
Yes, sir.
Hello?
Yes, sir.
So it is another method. It's okay. To solve this problem. Next is another important thing is action angle variable. Though these two chapters are very difficult, but we can solve some problems using this, which is generally asked in your examination. Um, okay. Another method, action angle variable in systems of 1 degree of freedom. For periodic motion, both libration and rotation. You have see libration, rotation means this makes this wave type sine cos wave. Libration means repeated motion, maybe circular, parabolic, okay, circular, this type of libration or this motion. Rotation, we can introduce a new variable j uh, designed to replace the transform constant moment alpha. Okay. J is equal to, actually we divide the whole on the action variable. It is nothing but integration of P dq. Since we plot phase space diagram, phase space means one axis Q, another axis P and Q. Okay. So it's in, if the diagram is this, then the area covered between this is integration of this P dq closed path. This is actually action. Integration of P dq. In phase space, our axis is one P and our Q. Where integration to be carried over complete period of libration or rotation. Okay. J always have the dimension of angular momentum. Here J has dimension angular momentum. Now from Hamilton-Jacobi theory, we have S is equal to WQ alpha minus alpha t, and H is equal to minus del S by del t, which is equal to alpha. P is equal to del S by del Q. Here you can say del W by del Q, because here Q is absent. You have to remember these three formulae for Hamilton-Jacobi theory. Now we use this formulae to get the action angle variable. So Hamiltonian is a function of QP. But Hamiltonian equals alpha, so alpha is a function of QP, which implies that reverse case P is a function of Q alpha. Okay. QP is alpha, so P is a function, we can write P. QP means got some function of QP. So let's say Q square plus P square by 2m is equal to alpha. So obviously you can say P is a function of alpha and Q, because P square is equal to 2m into alpha minus Q square. So P is a function of Q alpha. So if P is a function of Q alpha, then what is J? J contains PQ dq integration. So J is a function of Q alpha and integration over Q. Integration over Q means, you know, there is a if it is a limiting case, you put limit in place of Q. Our result is without Q in general. Since limit is given, in closed path also we have put the limit. Suppose closed path means if a circular path, if you put angle 0 to 2 pi. Okay. So then actually in place of Q, it integrated PQ. In place of Q, you put the value. So in the result, only P is present, no Q. So again, P is a function of Q alpha. Since Q is integrated only alpha, so now our J is a function of alpha only. So we can say in reverse way, alpha is a function of J. And say Hamiltonian relates this, so we can say alpha can be written as a Hamiltonian as a function of J. Alpha is equal to Hamiltonian, so we can say it is a function of J. Okay, are you getting my point? This is somehow easier using the formula. Hello?
Yes, sir.
Uh, so this is your alpha. Now we already know this is WQJ, Hamilton's characteristic function W is a function of QJ. Now we define a quantity which is known as, actually you can say, frequency or angle variable W, which is related with corresponding angular momentum. Okay. We consider coordinate. You know Q is related with P. Q we cannot get variable Q. So Q dot is equal to del H by del phi. Similarly, in case of angle, we take angular velocity, angular omega. angular velocity omega means angular displacement derivative omega, it must be equal to corresponding p. We take is angular momentum j, so some quantity derivative we take as a w here. Okay, so this is an angular variable. This one, since q dot del h by del p, w dot del h by del j, similar to this formula, we can also write q dot w dot is equal to del h by del j, angular momentum. H is now written a function of j, which is actually frequency nu j. So w is equal to integration of nu j into dt. We can say nu t plus beta. So change in w, because change, slight change. Here integration is our complete cycle. So del w we can write actually del w by del q into dq. It depends on q over complete cycle. So you can write the change in w as q goes through a complete cycle of liberation or rotation. So del w is nothing but the change in w as q goes through a complete cycle. We write like this: del w by del q into dq integrate over complete cycle. But w is equal to del w by del j. So this is our equation. So del square w by del q del j is equal to dq. Since j and q are independent variable, j and q do not depend on each other, so you can interchange this variable. So I can take and integration is over del q. So I can take del z outside it. So I write it del by del j of this, which is written here. So substitute del w by del q is equal to p. We have del by del j p dq. But by formula j is equal to integration of p dq. So putting j by 1. So del w get 1. And w changes by unit as q goes through a complete period. This is the conclusion. So del w is equal to 1, but w is equal to nu into tau, the frequency in time period. So from this equation we can say frequency is 1 by time period. You also know classical that relation. So now we can say nu is equal to del h by w day. Nu is nothing but del h by w del j. This is the formula. Basing on this formula, we have to work actually. Frequency is nothing but del h by del j. This is one example, similar harmonic oscillator. Here h we already know, j integration of p dq. So from here you can get p as this 2m h into h minus half m square minus q square root over. Putting h is equal to alpha, we can write 2m alpha minus m omega square q square. Q is equal to root over of 2 alpha m omega square sin theta. We know from last problem, simple harmonic, we generally know something into sin theta is sin theta. Putting that, you have to find and integrate j. J value will be 2 tau. So 2 tau alpha by w. So alpha is h. So j is equal to 2h pi by w, or putting nu is equal to del h by del j. We found here nu is equal to omega by 2 pi, or nu is equal to 1 by 2 pi k by m root over. The general formula you already know that. Generally we use this in our problems. Suppose a problem is given, its potential is a x to the power 6. Question is, if total energy particle is E, then find its time period. We have used the simplest formula that nu is equal to del h by del j. This one formula which is in problem. Nu is equal to del h by del j. So time period is equal to reverse del h by del j, but j is equal to integration of p dq. Okay. If potential a to the power x6, you know, half kx, so ax square. How you plot this ax square, which is for harmonic oscillator? Here we get a ellipse. So all x for ax to the power 4 also similar type of x to the power 6 also similar type equation. For ax square we have equation p square by 2m plus half k q square is equal to Hamiltonian or total energy E. Or you can say P by 2 me root 2 over P square by 2 me root 2 over square plus Q square divided by root 2 over of 2 uh, by E k. So k, so 1 by k, 2 by E. E here, 2 E by k, sorry, divided by 2 E by k. Root 2 over, whole root over, or a square. Means I divide E in every term, so it will be E divide again k, I divide k here. That means 1 by k multiplied with 2k. So 2 by k square is equal to 1. So basically it represents a ellipse. One axis is A is equal to 2me root over, B is equal to 2me root over, B is equal to root over 2e by k. Generally P is Q axis. So you can say here in P axis this A is nothing but root over of 2me. So for x square you 2me and Q is equal to 2e by k root over both together root over of E. 2e by k root over. Now our potential is x to the power 6. Okay. Here. So we can write JPQ. It is also ellipse P. Ellipse its area is equal to pi PQ. And root over is 2me root over one side. Another side is E by A to the power 1 by 6. Otherwise it cannot be ellipse. If we add x to the power 6, x to the power 1 by 6, so axis is 1 by 6. Here it is a half 1 by 6 area. Uh, so you 6 add this half plus 1 by 6. What is the result? It will be half plus 1 by 6 means 6 3 6 2 3 so 1 4 4 by 6 2 by 3. So power it varies like 2 by 3 j. So time period del j by a varies like e to the power minus 1 by 3. Similarly, there are another problem where alpha x to the power 4 q to the power 4. 4 means 1 by 4. It varies one axis to me, another varies from e to the power 1 by 4. If you add this half 1 by 4, you get 3 by 4. Okay. Similarly, here x to the power 2n. 2n means varies as e to the power 1 by 2n. So putting this formula, okay, these are the formula action angle variable. You can see into some problems. One, okay, you can do it easily. So this is all about your action angle variable and Hamilton-Jacobi theory. Both theories are somewhat difficult, but you can do problems on it. Generally, problems are asked in your examination. Uh, okay, if you see this material, then you can solve some problems on it. Okay. Next, we go for rigid body dynamics, something which is very important. Rigid body dynamics. Recovery. Okay, we discuss some problem with rigid body. Rigid body one. For the kinematics of rigid body. Okay. So rigid body means uh, the distance between any 2 point is fixed. Rigid body slide is visible. Hello.
Yes, sir.
Uh, okay. It's a new one on it. Actually, part four, which is very important part. So rigid body motion. Rigid body means about the distance between any 2 point of the body is fixed. Suppose this body, the distance between, let's say, A B is fixed, AC is fixed, AD is fixed, BC is fixed, BD is fixed. So when we construct a body, suppose when we take one particular, let's say A means in space it needs three coordinates. When we take another B point, then B needs also three coordinates. But one thing is, if it is rigid body, the distance between two is fixed. So one constant comes here, so one degree of freedom decreases. So we only need extra two coordinates to know this system. Again, if you take another body C, for C we want also three coordinates, but AC is constant, BC is constant in the rigid body. So we have two constants, so we need only extra one coordinate. If another point D is here, then we need three coordinates for B. D is constant, A D is constant, C D is constant. But there are three conditions, we reduce it to zero. If you move another more number of particles, then also you get 0, 0, 0. So its degree of freedom is 6. For a rigid body, we need 6 independent coordinates to solve its problem. Okay. So how it is actually done when you compare to a rigid body motion? Actually, we set a axis inside the rigid body, which is known as body set of axes. We have an axis x, y, z, which is called space set of axes. We set the body set of axes. Uh, if we define its position, origin of the body set of axes, it needs three coordinates x, y, z, and according to this the body is rotating about this origin, so three angles alpha beta or phi theta psi, but in Euler angles. So these are can be treated as six coordinates for the rigid body. Three are the coordinates of the origin of the body set of axis, other three are angles. Okay, we will discuss all this in this unit, and in this block. For rigid body. A rigid body is a system of mass points subject to the holonomic constant that the distance between all pairs of points remain constant throughout the motion. The equation of constant for a rigid body have the form Rij is equal to Cij. Distance between any two points is fixed. Rij means distance in ith and jth particle is equal to a constant. To fix a point in the rigid body, it is not necessary to specify distance to all other points in body. We need to state the distance of any three other non-collinear points. Thus, once the position of the three of the particular rigid body are determined, then constant fix the position. Okay, 3, 2, 1. Or if you know the 6, then everything is fine. The number of degrees of freedom can't be more than 9 by definition. If 3.3 maximum, 3 for A3 or B3 plus 3. But there are three constant or conditions, we reduces to 6. But there are three equations, we reduces the degree of freedom as 6. To following consideration also tell the only 6 coordinates are needed. What I told, if you take first point 3, 2, 1, so 6 coordinates are needed. Also, there may be additional constant on the body beside the constant of rigidity. Suppose one point of rigid body is fixed, one condition. If one point is fixed, then 3 coordinates are given. This is fixed. So, according to this, you can find 3 coordinates. So, only 3 coordinates are more needed to define the system. These three are actually angles. Okay. Again, the rigid body, what I tell you, if one point is fixed, and 3 of the coordinates needed to specify the coordinate origin of the body set of axes, the remaining 3 are angle. What I told, among the 6, this is body set of axes, we need origin of this coordinate axis and these angles. There are many ways of specifying the orientation of Cartesian set of axes to another with common origin. Okay. Let's say that is the body set of axis is a prime system, space set of outside axis, our axis x, y, z is an observer is present in unprime system. So we have to see the rotation of this body, 3 parameter. For knowing the rotation, we have to fix the origin. Let's say we set a coordinate axis with z, x, y look like this. This axis, see. Y is parallel to this, Z is parallel to our space axis, X is parallel to the axis. Then only we can measure the angle of rotation. What is the angle of rotation of their body set of axis? Okay. Which can we actually find in terms of direction cosine? So you know the angle between these two, prime and non-prime system. And cos theta 1 is nothing but angle 1 means it is angle between cos of prime on prime. First one is prime, second one on prime. 1 2 I 1 is first coordinate x coordinate, 2 for y coordinate, 3 for z coordinate. Actually we write x1 means x, x2 means y, x3 means z. Okay, in this way. So 2 1 means j I cap angle. Not round angle. From this we can actually see how the transformation occurs between two space set of axes, which particularly given by Euler's angle. But one thing here, remember that this transformation is orthogonal transformation. Transformation from space set of body set to body set is orthogonal transformation. It can be represented by orthogonal matrix, and in orthogonal matrix we know there is a relation exists. If A is orthogonal, A into A transpose is equal to identity matrix. So transpose is equal to its inverse for orthogonal transformation. And if you see what is the A at A is equal to 1, so it's represented transformation. Then if you take a determinant of A, and determinant of AT is equal to 1 because identity matrix determined 1. If you change the rows to column, then you got transpose. How determinant of transpose is related with determinant of original matrix? Okay, tell me, is there any relation we can find determinant of a transpose matrix with determinant of original matrix? Is there any relation? Hello? Hello? Hello, am I audible? Transpose means we only change rows to column. Is determinant is changed by changing row and column? No, it is not close to. Hello? Any idea? Am I audible?
Yes, sir. Yes, sir.
So if you change row and to column, column to row, then actually determinant does not change. AT determinant is same as A determinant. So that means we can say mod A determinant square is equal to 1. Then what is the value of determinant A? If it is 1, it will be root over of 1 means it is plus minus 1. If determinant is plus 1, we call it a proper rotation, which actually describes the rotation process. And if it is minus 1, we call it a inversion. It is if mod A is equal to plus 1, proper rotation. If minus 1, then we call it inversion, which actually invert the space coordinate or spatial inversion. Mirror symmetry, inversion mirror symmetry. X, Y, Z make by minus X, minus Y, minus Z. Okay. Okay, the condition I will not go to the details. Only remember that the orthogonal transformation. Okay. So the orthogonal matrix are to apply. For orthogonal transformation, we have this. Where is that? Okay. But transformation is orthogonal. Only remember that. So whenever transformation we get, it is orthogonal one, and you can say proper rotation, proper orthogonal, determinant 1. Okay. Now we go for Euler angles and Euler theorems, which are very important. Uh, Basically, the three independent parameters which would completely specify the orientation of a rigid body about a fixed point. We know it needs 6 coordinates. If one point make fixed, then we it's the x, y, z fixed. So we know 3 coordinate by this. Only 3 coordinates are needed. So if in a rigid body one point is fixed, then we only need 3 coordinates. Generally, we take the fixed point at center of mass, which is treated as the origin of the body set of axis. Okay, and the three angles are known as Euler angles. Euler angles are the three successive angles of rotation, not any arbitrary rotation. Successive angles of rotation arise due to three successive rotations performed into a specific sequence for transforming a given Cartesian coordinate system to another. So Euler angles are used to transform one Cartesian coordinate to another in a specific sequence. In other words, we can get body set of axes of a rigid body which is attached to the body from space set of axes where object is present by three successive rotations known as Euler angles. It is a process. For this, let x, y, z be the orthogonal space set of axes with unit vector I cap, j cap, k cap in the space. For body, we take x prime, y prime, j prime, whose axes are I prime, j prime cap and k prime cap. And you take 3 rotations. First rotation is space set of axes rotated through angle phi. X, Y, Z is rotated through angle phi. Okay, about Z axis. You know in rotation, axis of rotation remains fixed throughout the rotation process. If you rotate about Z axis remains fixed. X, Y only changes through an angle phi. Okay. Now, so you can define new unit vector, which is I1, J1, I1 is equal to how much? Here you can say cos phi I cap plus sin phi j cap. J1 is equal to minus sin phi I cap plus cos phi j cap. K cap remains fixed, K cap is equal to same K cap. So basically this is the matrix cos phi sin phi minus sin phi cos phi 1 is the rotation matrix you know. Okay, so I can write new 1 is equal to this rotation matrix in 1. K remains fixed, so K axis 1, 0, 0. Other cos phi sin phi minus sin phi cos phi. Okay, let's say it as D. Then a first rotation, second rotation through an angle theta. Let's in second rotation the intermediate axis xyz, this one. About this axis, we want new x1. We rotate through an angle theta such that the new, so z will be rotated through theta, and this y will also rotate through theta. New z is nothing but the body z prime axis. Okay, In this rotation, actually, we keep x-axis fixed, so only y, z are varied. So x-axis fixed cos theta sin theta minus sin theta cos theta. Okay. In third rotation about the new z-axis, already we get the body z-axis. We need only body x and z prime, x prime and y prime. For that, we rotate through an angle psi. If you rotate about body z-axis through an angle psi, I mean z-axis remains fixed, x, y changed by psi. Then the transformation matrix just like same first case, only angle is psi. Okay. So, but we have to perform in specific order. First phi rotation about body z-axis, then theta rotation about new x-axis, psi rotation about new z-axis. So if DCB, so order is like this DCB. So a total complete operation, if you can say A, so if you define A actually nothing, A is equal to B, C, D into I cap, J cap, K cap in the reverse way. If a transformation A makes it, then A is equal to B, C, D, I cap, J cap, K cap. So x prime, y prime, j prime equal to A, x, y, z means x, y, z is equal to A inverse x prime, y prime, j prime. So you can calculate A multiplying B, C, D. These are the multiplication. So these are the three transformation matrix which are very important. Sometimes asked in your examination. Find the three Euler's angle phi, theta, psi. Okay. Is it clear? Hello? Hello?
Yes, sir.
So since it's a transpose matrix, you know A transpose, sorry, orthogonal matrix, A transpose is equal to 1. What means A transpose is equal to A inverse. So B transpose B inverse, C transpose C inverse, D transpose D inverse, or if you see A whole transpose B C D transpose, find is equal to also A inverse. If you find A, then you can write also A transpose or A inverse. Then Euler's theorem motion of a rigid body, it tells that the general displacement of a rigid body with one point fixed is rotation about some axis. The displacement mean of a rigid body means if one point you take fixed, then displacement means nothing but rotation. It is somehow analytical proof using the two property of rotation. Rotation has two important property. What are the property? One thing is rotation, axis of rotation fixed, and magnitude of the vector does not affected by the rotation. If somehow the vector, if you rotate it, its direction changes, but magnitude of that vector remains constant. So if one vector lies in an axis of rotation, uh, then it remains already invariant. The vector of itself remains invariant. Okay, that is the proof here. So analytical sense. So let's from here that the magnitude of vector is unaffected is automatic by the orthogonality condition. If magnitude of vector is remains invariant, we know if it is axis of rotation, then in that direction vector the axis remains invariant. Though it is transform A R prime, but if it is axis, then R prime is nothing but same R. Okay, Euler theorem will be proved if we prove R prime is equal to R. R prime is a new vector which comes from transformation of R, but one R prime must be equal to R. That is the condition, because that is axis of rotation which remains invariant. Okay, but this equation looks like a eigenvalue equation. R prime is equal to AR is equal to lambda R. So our now aim is to show that lambda is equal to 1. Characteristic value lambda is equal to 1. An eigenvalue problem. Okay. So how to prove this lambda is equal to 1? So if you this from this equation R is AR is equal to lambda R. So A minus lambda is equal to R, or A minus lambda I unit matrix I multiplied is equal to R is equal to 0. We have to show that one of the eigenvalue is equal to 1. A minus, if I expand it, I can write it R means X, I cap, Y, J cap, Z cap, matrix term X, Y, Z. So A11 minus lambda, A12, Y, because it is a unit matrix multiplied. So when lambda when multiplied to 1, 0, 0, and 0 1 0 0 0 1. So it will be only lambda if 1 1 lambda, 2 2 lambda, 3 3 lambda. Otherwise nothing. Right, like this. Okay. So now I have to prove 1 lambda is equal to 1. This equation, which is known as secular equation matrix, A minus lambda I is equal to 0. Characteristic of secular equation. Our aim is to get 1 lambda is equal to plus 1. I will solve. For this, actually we have to use the orthogonality property of this matrix A. A is a orthogonal matrix, means its transpose is equal to inverse. So this thing. So A minus 1 into A transpose. A into A transpose minus A transpose. But A into A transpose 1 minus A transpose. If we take determinant of both sides, determinant of this must be equal to determinant of this. But A minus 1 determinant into AT determinant is equal to 1 minus AT determinant. To describe the motion of rigid body, the matrix A must correspond to a proper rotation. Therefore, A and its transpose must be plus 1. Okay. We know that A transpose is plus 1. Further, since 1 is a diagonal matrix, A and A transpose are same diagonal element. So the transpose sign equation here actually 1. A will subtract from 1. 1 is a diagonal matrix. So A minus 1 means it only diagonal matrices are affected. Here also 1 minus A. We know A transpose determinant same. Now in the case A minus 1, 1 minus A. Okay. If A is a orthogonal matrix, proper orthogonal matrix, then determinant of A is equal to 1. We see already, because A transpose 1 means A transpose A, so A square 1, A is equal to plus minus 1. If it is proper rotation, A determinant is plus 1. But A determinant is equal to A transpose A determinant, so this is equal to 1. Now something into 1 means that we got A minus 1 determinant is 1 minus AT determinant. But AT determinant same as A. It is not 1 minus. So 1 minus A minus 1 determinant is equal to 1 minus A determinant. But actually if you A minus 1, 1 minus A means a minus. A minus 1 is equal to minus of A minus 1. Isn't it? So we see the determinant of some quantity related vector V is same as determinant of minus V. Then what it means? If someone is its negative, basically 0. 0 is its own negative. But formula we have determinant of minus V is minus 1 to the power n B. N is the order of the matrix. Here 3 cross 3 matrix. So minus 1 to the power 3 order V means minus V. If B determinant is equal to minus V determinant, then we say it is nothing but 0. That means this term is 0. A minus I is 0. So if you take A minus lambda I is 0, then A is equal to lambda I plus, which implies lambda is nothing but plus 1. So this theorem is called Euler's theorem. Here we prove then one eigenvalue is plus 1. It's somehow analytical, but easy. You can prove this. Okay, that is some more common, more general displacement rigid bodies. Total displacement translation plus rotation with Chasles theorem. Is it okay this? Hello? Hello? Hello, any problem? Another? Hello?
Yes.
Next we go for the properties of the matrix, which is very useful. You also know most of the properties, uh, properties of the transformation matrix. Okay. We basically, what we already discussed, that is orthogonal transformation A transpose 1. I am not repeating that. Another A transpose 1, A square 1. Okay. A mod square A is plus 1 or minus 1. If minus 1, we call it inversion. Inversion means, imagine some matrix to determinant minus 1. Simplest one is this type of matrix, minus 1, minus 1, minus 1. So it diagonal element, three diagonal elements are minus 1, off diagonal 0. So if you take a determinant, you take minus 1 into minus 1 and plus 1 minus 0. So it will be nothing but minus 1. So simplest matrix is this. Suppose it is multiplied with some function. It is multiplied with x, y, z. What you get? You get actually minus x, minus y, minus z. Is not it? Hello? If we multiply s with x, y, z, minus 1 x, minus 1 y, minus 1 z. This type of transformation is known as spatial inversion. Okay. And spatial inversion can be achieved in classical. In quantum mechanics, it is called parity. I think you heard this word in nuclear physics or quantum mechanics. Parity is a property of quantum particle. Parity. Though it has no classical analog, but you can say comparing, it is nothing but classically called spatial inversion. A space coordinate becomes opposite. Parity means what? If we operate on R, it gives you minus R. X becomes minus x, y becomes minus y, z becomes minus z. Classically also we can achieve same cases. Suppose we rotate one coordinate system by 180 degree about its z axis and then reflect in the xy plane. Suppose this is our axis x, y, z. If I rotate about z axis, z is fixed. Yz changes by 180 degree. That means my new one is y is in this direction. Z is fixed. X is in opposite direction. Now I take reflect in the xy plane. Means reflection of z axis. So z axis reverse z. So it is just its opposite. X minus x, y minus y, z minus z. This process is called inversion or partial inversion. Okay. It is improper transformation. Actually, this is called parity in quantum mechanics, and under parity, actually all interactions basically electromagnetic strong interactions, they are invariant under parity. Also gravitational interaction, only weak interaction parity violates. In our book, we only discuss mechanics, all mechanical forces, gravitational forces, electrodynamics, all these things. Nuclear physics. Nuclear physics strong force come under. And mechanical forces are actually electromagnetic origin. All forces in mechanics are electromagnetic forces origin. So they also wave parity is conserved. So every equation what we see in our book, there is a conservation of parity in those equations. Parity conservation means you can say scalar and vector. Scalar, a quantity scalar means how you define scalar and vector.
Scalar has only magnitude,
Vector as what's
magnitude and direction.
So what about current?
Current has a
Scalar
direction.
quantity.
How we say current as a direction?
The direction of opposite to electron.
We call current as a direction. Why it is a scalar quantity? True, it is a scalar quantity. Why? Okay. To remove this type of ambiguity, actually, we can slightly define a new way. Suppose the scalar quantity is mass or anything scalar. If you rotate it, then it
The
remains
coordinate
same 5 kg.
current scalar is vector.
Okay. in rotate it, 5 kg remains 5 kg. If you suppose this is a vector, I rotate it through an angle, I get this vector. Let's say A prime. Does A and A prime are same? Because you say vector has direction. Now direction changes. Not it?
Yes,
So
sir.
now you can define vectors changes due to rotation, but scalars remains invariant on rotation. So scalar quantity is known as rotational invariant quantity. Rotational invariant quantity or scalar quantity, or you can say the physical quantity which remains invariant under rotation, they are scalar. Which changes under rotation, they are vector. Rotational invariant scalar and varies vector. Okay. But another if you had word pseudo scalar, pseudo vector, or axial vector.
Tensor.
Uh, no, I am not going to tensor. Actually, vector is just tensor of rank 1. Pseudo term, pseudo scalar, pseudo vector, or axial vector, they actually define in terms of parity. In general, scalar has positive parity. Since it is not affected by rotation, x, y, z coordinate does not change. So, under parity inversion, it remains same, scalar. But vector changes direction. So it has x, y, z, I cap, j cap, k cap. It will be changed. If we multiply minus, it will minus. So vector has negative parity, means if we change f of r, it will be this one minus r. But scalar does not change. So scalar has positive parity, but vector has negative parity. But there are some scalars which is invariant under rotation. They have negative parity. They affected by the parity. They are called pseudo scalars. Particularly triple product of vector, a scalar triple product. You see in mathematical physics, you know a scalar triple product. A dot B cross C. You know it? It is a scalar or vector?
It is a scalar.
Scalar triple product, because when it is cross product gives a vector, vector dot product is scalar. But see, suppose this vector changes under parity, it gives minus 1. This vector changes under parity, gives minus 1. This vector changes under parity, gives minus 1. When we multiply 3 minus 1, what is the result?
Minus.
Minus 1. So we get a scalar with minus 1 parity, with parity opposite. That type of scalar actually pseudo scalar. Okay. Similarly for vector, there are some kind of vectors whose parity is positive. We call them pseudo vector or axial vector. Okay. Pseudo vector or axial vector, positive. They are actually rotational terms. Suppose angular momentum L is equal to R cross P. Product of two. So R is a vector, it has negative. P is a vector, it has negative. So negative into negative, positive. So L has positive parity. Okay. So parity is in this way important, or spatial inversion is in this way important. You have to remember how now R position vector is a pure vector, a negative parity. And all other derivative of R also negative parity. So from any equation of your book, you can check the parity of quantity, because parity is conserved in all interactions which are written in book except weak. But weak is not written in your book on that interactions. So all interactions what you study in class 3, all equations particularly, they are invariant under parity. Means you can check left hand side parity or equal to right hand side parity. Well, if that is what you can say, but is not your syllabus. Hmm. Then these are matrix properties I am focusing, because these are very important properties of matrix. If you know these properties, you can solve all matrix related problems. If it is an orthogonal matrix, we will discuss A inverse is equal to A transpose. That means A transpose A is equal to 1. Similarly, if A is equal to A dagger, we call Hermitian or self-adjoint matrix. Dagger means transpose of the complex conjugate. Isn't it? Hello?
Yes, sir.
You will say with what quantum mechanics, Hermitian transpose of the complex conjugate. If A is equal to A dagger, we call this self adjoint or Hermitian. If A dagger into A is equal to 1, hello? If A dagger is equal to, that is A dagger is equal to A inverse, then we call it unitary matrix. Why the term unitary matrix is used? Because their eigenvalue was unimodulus. All its eigenvalues, whatever of a unitary matrix, if you take a modulus, all have one, unimodulus. Okay. All real orthogonal matrices are unitary. Dagger and transpose difference is complex. If it is real, then dagger is equal to transpose. So all real orthogonal are unitary. Again, lambda is the eigenvalue of a matrix. Then Ax is equal to lambda x. X is the eigenvector, you know. Lambda can be found as the root of the characteristic equation A minus lambda I mod is equal to 0. Where you see it. For n cross n matrix, there are n eigenvalues. Depending on order, there are n eigenvalues. The product of all eigenvalues of matrix is equal to determinant of the matrix. Suppose it is 3 cross 3 matrix, 3 eigenvalues. If you take product lambda 1, lambda 2, lambda 3, you get determinant of that matrix. Similarly, if sum of all eigenvalues of matrix equal to trace, if you are lambda 1 plus lambda 2 plus lambda 3, then it is get trace. Trace means what? Hello, trace means? Hello? What do you mean by trace of a matrix? Sum of all diagonal elements. So if you add sum of all diagonal elements, then diagonal you get this. The trace of a matrix is sum of diagonal elements. So the eigenvalues of a diagonal matrix are its diagonal elements. If your matrix is diagonal, then its eigenvalues are its elements. Because diagonal means subdiagonal 0. Since trace is sum and product is determinant, so obviously this is the matrix. For that reason, we are generally diagonal is a matrix. Another thing, sir, if lambda is an eigenvalue of A, then lambda inverse is also eigenvalue of A inverse. And lambda to the power n is eigenvalue of A to the power n. Okay. If lambda is A, lambda inverse A inverse lambda n A to the power n. If A, B are two square matrices, then AB and BA have same eigenvalue. For a symmetric matrix, A transpose is equal to A. For anti-symmetric, A transpose minus A. Or skew symmetric. For real symmetric matrix are Hermitian and real anti-symmetric matrix are anti-Hermitian. The eigenvalues of Hermitian matrices are all real. And eigenvalues of anti-Hermitian matrices are 0 or purely imaginary. Unitary matrix means the eigenvalues are modulus is unity or 1. Any two eigenvector correspond to distinct eigenvalues are Hermitian. Of a Hermitian matrix are orthogonal. For a non-singular matrix, non-singular means determinant is not equal to 0, then we have a similarity transformation A is equal to P inverse AP. And for similarity transformation, determinant are both same, trace is same, so eigenvalue are same. Okay? These are the some properties of matrix. Using this, you can solve many matrix problems. I have a set of problems actually. If you can do using these formulas, you can solve this. These are the properties. You can solve this problem. Okay. Using this property, you can solve all problems. Okay. I am setting a problem. Okay.
Sir, one doubt.
Huh. Tell me what is your doubt? Hello? Your voice is not clear. Please tell-
Sir, when we derive Lagrangian from Hamiltonian principle,
uh,
the variation of a generalized coordinate at the end points is 0. Why?
what means?
The variation in generalized coordinate at the end points
Uh,
at T1 and T2 is 0. Why, sir?
0. Why? T1, T2, there are many paths between 2 points. Suppose 1, 2 points. Huh?
Yes, sir.
Variation means what? Change. Okay?
Change.
Each 2 points are fixed. What is the change of a fixed thing? Tell
0.
me. Uh,
0.
So when
Constant
it
0.
reach here, you are telling from suppose it is going to up, going T2. After T2 there is no motion. So delta when it is T2, if you take delta T2, it is 0. There is no motion beyond T2. Similarly, when falling down T1, 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 when at T1 it has no further downfall. Delta to T1 is equal to 0.
Yes, sir.
Because there are two fixed points. Motion is a constant between these two regions. Or you can say boundary of a wall. How it goes, if it reaches boundary, where it go?
No change.
Okay. So there is no change. QP.
Okay, sir. Okay, sir.
Okay, we will discuss next in the next class tomorrow. Okay.
No.
Only 5 students are joining. Okay. Okay. Okay, I
Okay,
am
ma'am.
sending the slides. If any problem, you can ask me. And that group also personal WhatsApp group. Okay. Okay, thank
Thank
you.
you.